So if you look at the different character tables, if you're perusing them in the back of a book or on web campus or online, you'll notice something odd with some of the character tables in that there's actually imaginary numbers or even complex numbers. Numbers, remember, are numbers that have both real and imaginary components. And so remember, I is the square root of -1, and that's an imaginary number because you can't, with real numbers, take the square root of -1. But in math, imaginary numbers are still very important, right? So we're gonna kind of say why this is, or go into why this is. None of this video's content do you have to worry about for the exam. It's mostly to satisfy your curiosity, since you'll be dealing with some of these character tables throughout the course. So you'll be wondering, why are these strange imaginary characters popping up? So the C4 character table is one of these examples. And it has these eyes in here. And this you have 4 classes, and you only have 3 vectors, but the second, the E irreducible representation is actually broken up into 2 components. And these have imaginary values in them. These are the point groups that have imaginary characters. It's the CN point groups, CNH, SNT, and TH. So these are actually fairly rare point groups. And a lot of these are chiral. Actually, all of them are chiral. So let's look at trying to derive this C4 character table to see if we can figure out where these imaginary numbers come from. So we would come up with these symmetry operations. We could use the rigorous definition of the classes to figure out that all 4 symmetry operations are in unique classes. We did that in a previous video. And so we're going to now, we've put down the totally symmetric irreducible representation of all 1s. We're always going to have that totally symmetric one. And now we can ask how X and Y transform. So with the identity, X is going to go to X, Y is going to go to Y. We have, if we're thinking that, we're setting up here thinking that these are going to transform together. So we're going to have a 2x2 matrix. We can't use block matrix multiplication to separate them. And this shows you right here, when you do C4, why they transform together. X is going into, if we do an X vector, rotating is going to go into -Y. And Y is going to rotate 90 degrees into X. So they're transforming into one another, so we can't break them up. That's going to be your matrix for X going into -Y. Remember, this is times by and a 2x1 XY vector. Y goes into X. And you can do this for C2. It's 180 degrees. X is going to go into -X. Y is going to go to -Y, excuse me. And so you're going to get that matrix. And you can again do this for C4-3. X is going to go all the way to Y, and Y is going to go 270 degrees all the way to -X. And you're going to get that 2x2 matrix. And so with all that being said, now you can figure out the characters right from the trace. So for identity, it's going to be 2. For C4, it's going to be 0. For -1, it's going to be -2, right? -1 plus -1 is -2. And for C4-3, it's going to be 0. 0 plus 0, 0. So at this point, it's like, where are these imaginary numbers coming from? Right now, it's not quite obvious. So what you can do is now you can write down that irreducible representation, 2, 0, -2, 0, and then use one of your other rules to find the other vector. And so if you do this, checking to see that everything is orthogonal, you can get 1, -1, 1, and -1. And so everything looks good. Most of our rules are satisfied. We can assign the Mulliken symbols, A or B because of a dimensionality of 1, and E because of dimensionality of 2. And then that's basically it. And A because we're symmetric with C4, principal rotation axis, and a -1 gives us a B for the second irreducible representation. The problem though is if we check our 4 rules, you'll quickly see that rule 1 isn't obeyed, right? Rule 1 tells you that the sum of the squares of the dimensionality has to equal the order, and the order is 4, because we have 4 symmetry operations, 1 plus 1 plus 1 plus 1, and 1 squared plus 1 squared plus 2 squared is 6. So the only way mathematically to overcome this problem is to use imaginary numbers and break E up into basically 2 components. That also gets you solved. That also allows you to have 4 irreducible representations here effectively, right? And you know that from rule 4 of the character tables, we always have to have the same number of rows as we had to do columns. So now we have 1 squared plus 1 squared plus 1 squared equals 4, and that equals the order of the group. However, with imaginary numbers, some of the things really change, some of the rules kind of change. So there's a special 5th rule that I like to call a special 5th rule for imaginary characters. Again, all this is kind of optional material just for your curiosity. For each component, the sum of the squares of each character multiplied by the number of operations in that class is actually going to be equal to 0, okay? But for the components together, the sum of the squares of each character multiplied by the number of operations in that class is equal to twice the order of the group. And this is just because there's 2 components. And so just to show you that, here's rule 5. If you add the components together, that's where if you add these components together, we broke it up. That was originally what we had. But if you add those components together, you'll get back 2, 0, negative 2, and 0. And so with rule number 5, because there's two components in this vector, essentially you're going to have to go 2 squared, square these all up, and times by the number of symmetry operations. There's 1 in each class. That should equal the order using a normal rule, but because this is a vector that has two imaginary components embodied in it, it's actually this value equals not 4, but 2 times 4, 8, because there's 2 components. So that's rule 5. If you want to actually derive the characters in there, how did I get the i's and the negative i's, etc., you're going to have to use block matrix multiplication to reduce these into 2 components. And so in order to do that, then you're going to have to set up variables here, basically to figure out what values can allow you to break this up, right? So in order to break this up, you have to have zeros on the off diagonal. So E is fine, C2 is fine, right? So I'm trying to break this up into vectors with 1 dimensionality. So that tells me I have a 1 and 1 here, 0, 0. So that gives me a 1, 1 there. And this C2 is going to have negative 1, negative 1. I have zeros here, so that gives me negative 1, negative 1. But now I need some numbers. They're going to be imaginary numbers. That's the only way mathematically to do it, where I can have zeros here. So I'm basically forcing them not transform together, like what real numbers would say. With imaginary numbers, I can force them not to transform together. And so I'm forcing a 0 to be here, a 0 to be there. And so now you can basically run through some algebra, go through the different rules. And we know, right, that A1 plus A2, that's a trace, is going to have to be equal to 0 here. That's our unbroken up irreducible representation. B1 plus B2, again, that's a trace. That's going to have to be equal to 0. And we can use our rule number 5 and some other rules, rule number 3 here, to basically come up with a system of equations. And this gets, really detailed. I'm not even really going to go over this. It's just a bunch of algebra, okay? But you can solve these algebraic equations, and you can then get imaginary numbers out, okay? And you solve the values of A1 and A2, and A1 happens to be I when you go through all these algebra, okay? And B1 goes into negative I, and B2 goes to I. So that's where the imaginary numbers come from. One last thing, you'll notice some of them are even more complicated in the character tables, like for C3. they'll just show you epsilon, and then they'll tell you what epsilon is. Epsilon, they tell you, is e to the 2 pi I divided by 3. So it's 2/3 pi I and e raised to the e power. And then you have e asterisk. E asterisk, the asterisk in math means the complex conjugate. And that's the complex conjugate is when you take a complex number and you make the imaginary component the negative. And so you have to use Euler's formula. You may have learned this hopefully in some math class. Again, this is all details you don't really need to know. I'm just trying to share with you where all this comes from, and all the math and all the rules work out, even with these crazy imaginary numbers. So Euler's formula is this magical thing. You may have heard of this, you know, e to the pi I plus 1 equals 0. It's like this beautiful, one of the most beautiful formulas in math. YouTube it if you want to learn about the most beautiful formula in math. Some people say, right? E to the pi I plus 1 equals 0. It's connecting pi, you know, irrational number, e, irrational number, I, imaginary number, 1 and 0, fundamental numbers, right? So it is pretty cool. But anyway, that's a specific case of this general Euler's formula, which is e to the I theta equals cosine theta plus I sine theta. So that's where this comes from. So e to the 2 pi I divided by 3 gets you this. And the complex conjugate of that is the same number, so e star, which is this plus turned into a minus. And so all this works, all the vectors work, they're orthonormal, all the rules work, right? We have 3 rows and 3 columns. And so all those different properties work, but it's just a lot more complicated math. So we're not gonna worry about it in this course, but you know, at least now if you're curious, you know where this all comes from.